thanks for applying from this long distance. So today we're going to talk about Skyrmion, the Spin-Orbitronics and Orbitronics from both science and technology. That's right.
Okay, it's great to be here. It's actually my first time to Dijon, so I'm also sorry that I missed yesterday, but as Jana did get me here on time. But at least I'm here for my talk, which is great, and interact with you today. So in general, I'm going to talk about Skyrmions, but also more broadly about magnetic solitons. And I want to introduce not just fundamental physics, but also some device concepts. And then I don't really need to introduce any Skyrmions. There's been enough good talks about that. But I want to also focus a little bit on the fast dynamics as well as the thermally activated dynamics with the aim of using them in unconventional logic. So very quickly for devices, everyone knows the racetrack device. I used to work for IBM. And I was really excited about the racetrack at the time. There are also some ideas about magnetic logic and about sensors based on domain walls. And I just want to point out that while quite significant amount of money has gone into research on the racetrack, as well as into magnetic logic, the only device that I'm aware of that makes use of these topological solitons is actually this multi-turn counter device developed by a German company, Sensitech, that actually makes money, that actually is sold in the market. So, if we want to make these devices a reality, what do we need? Well, we need kind of two things that are important. We need to have stable bits. Okay, I think this pointer has just died. Are you sure it's manual? This never dies, but like. So you need to have stable bits because you want to obviously have information carried over a long time, and you need to actually manipulate. And so first, for the stability, what is the solution that we have in order to realize stable bits? So you all know Heisenberg's spin-spin interaction stabilizes domains with the magnetization pointing in a certain direction. However, for the Heisenberg exchange, by and large, it doesn't matter which direction the spins point in. So this stabilized states with random topology and random chirality. And well, what's the problem? This was very nicely actually already shown by Kapjin, that you can have these energetically degenerate domain walls. And if you have these domain walls with different chirality, then they can have the same topology as the uniformly magnetized state, and thus you have an elation of the two domain walls with no energy barrier, and so that's bad. So what we need is a way to stabilize only domain walls of one chirality. So here, of course, nature has something in store for us, the Jaruzelski-Maria interaction, which stabilizes two spins in a ferromagnet, not just directly as Heisenberg does, parallel or anti-parallel, but via a heavy metal atom, as shown here, for instance, platinum, and then you get an indirect exchange, and this indirect exchange favors not collinear alignment, but perpendicular alignment. And even better, it favors not just perpendicular alignment, but only this and not that. And so this means if you have perpendicular alignment like this, favored by DMI, and parallel alignment favored by Heisenberg, then you get some spin canting, and very importantly, going from left to right, we get a clockwise rotation of our spins. And that means this domain wall here is energetically favorable, because you can see that the spins go clockwise when you go left to right. This domain wall here actually is energetically unfavorable, because the spins, as you go along from left to right, go counterclockwise. And so this interaction stabilizes domain walls with a given chirality, and if you crank up the DMI further, you can get these Skyrmions, where again you see when we go from left to right that we go clockwise. Okay, and so this allows you to have chiral domain walls and Skyrmions that we have previously seen. All right, so now the first experiment that I want to show you is we want to check how stable are these chiral spin structures. And the experiment that we do is the following. We take our system, which is actually a striped domain state with chiral domain walls, and then we shake it. And we shake it by actually putting an infrared laser pulse onto our sample that just shakes all the spins. And then we use small angle X-ray scattering to detect the order of the collinear domains and of the chiral domain bonds. This can be done by looking at the sum and the dichroic signal in the small angle X-ray scattering. And then this allows us in a time-resolved manner to follow how well are the spins in the domains parallel and how well are the domain walls in a chiral fashion aligned. And so here is the result. We start before the pulse, perfect order in the domain, as well as perfect order of the domain walls. After 200 picoseconds, you actually, 200 femtoseconds, you actually reduce the order of both. And then actually after some time, the order comes back, and you can already see the order comes back a little bit different. And so here we now plot the order of the magnetic domains and of the domain walls, and we see both lose their order over a time frame of 200 femtoseconds, but then the domain walls recover more quickly. And I thought that's amazing, because DMI typically is only 10% of Heisenberg exchange, but still the domain walls recover 3 times faster than the domains. So the chiral domain wall structure recovers more rapidly than the collinear structure of the domains. So that means it's more stable to have our chiral domain walls than to have the collinear domains. And this was also recently confirmed in this paper here. So here are the 2 papers. So that's good news. It means we have stable spin structures, and the chiral domain walls are more stable than the collinear domains. And by the way, feel free to take pictures, take notes. I'm very happy to share the slides and have this posted, of course. Now we come to the stability of the Skyrmions. We already heard about what Skyrmions are. If you talk to a theoretician, you can discuss for a long time what a Skyrmion is. For a humble experimentalist like myself, it is a spin structure, as nicely shown by this animation by Felix Büchner, which you can map onto the unit sphere. So all the spins on the outside are mapped onto the North Pole. The spin in the center is in the opposite direction, is mapped onto the South Pole. And then something happens here at the equator, which determines the winding number of the Skyrmion. So there are different types of Skyrmions, which again Captain has nicely introduced. This Niel or hedgehog Skyrmion, the chiral or block Skyrmion, here more dipolar stabilized Skyrmion. But what is important is really this winding number, topological winding number n=1, because it is distinct from the uniformly magnetized state, which means you cannot destroy the Skyrmion by continuous deformation into the uniformly magnetized state. And just to show you that not all spin structures have that, again, Captain Mathias introduced that, you can also have this n=0 topologically trivial spin structure. And then this here can be continuously deformed into the uniform. And then reduces the stability. Let me show you. We apply a small field to destroy the Skyrmion, then we see this Skyrmion here is continuously deformed into the uniformly magnetized state. Now it's gone. So this can be killed easily, but our topologically non-trivial Niel Skyrmion just shrinks a little bit when we apply a field, but the topology stays the same. So that underlies this concept of topological stabilization. I don't like the term topological protection because it's infinitely protected only in a continuum model, whereas we live in a discrete world, so Bloch lines or Bloch points can always destroy it, but the energy barriers. So that's why topologically non-trivial Skyrmions have a high energy barrier, whereas the trivial Skyrmions have a low energy barrier to be destroyed. Now, this is all theory. Never believe a theoretician. Do the experiment yourself. So we did. Maybe too many theoreticians in the room. I should not have said that.
Big mistake.
Oops. Okay, let's also do experiments and see if theoreticians are correct. And so by now, there are many implementations of Skyrmions using multi-layer systems. I should point out early work by Axel Hoffmann's group. This was our work here, as well as by people in Grenoble and Paris. And meanwhile, there are many magnetic multi-layer systems, typically based on a heavy metal, a ferromagnet and an oxide. And they range from Skyrmions with a few tens of nanometers diameter to micrometer diameter. But what is important is that they all have the same topology. So qualitatively, their behavior is the same. And if you're interested, here are two review articles with some of this. And recently, we also went into 2D materials, and also we find that in 2D materials, we observe also Skyrmion spin structures in this iron 5 germanium telluride. They are non-chiral. In iron 3 germanium telluride, they're chiral. So have a look at the paper if you're interested. Okay. Now, Skyrmions are great, but they're even more interesting spin structure. So recently we started to work on Merons and anti-Merons. So here we have a schematic depiction of a multi-layer of 2 layers, a synthetic antiferromagnet, where the 2 layers are antiferromagnetically coupled. So here in the center spin up, here in the center spin down. Here the spins point from the inside to the outside. Here they point from the outside to the inside, so anti-parallel coupling. And then there are different types of spin structure that you can realize. And they're interesting because firstly, they are different ones, but also they are not isotropic in the plane, meaning there is an angular dependence of their properties which can be exploited. Now, the first step was to actually try and find these beasts. And so it's actually not that easy to find and to stabilize them. So we did a bit of engineering of the multi-layer structures. And then by a combination of in-plane imaging using SAMPLE and out-of-plane imaging using MFM, we can actually identify these spin structures, and we can determine their spin structure, their Meron nature, by actually finding the out-of-plane contrast with opposite contrast of the 2 spin structures, and here the in-plane contrast having either vortex or anti-vortex structure. And then we are able to identify that they typically actually appear in pairs, and that is again a result of their topology.
Is it plane magnets?
This is it's at the border. That was exactly the thing. So this is very close to spin orientation transition. So it's just easy plane, but has a large out-of-plane component. So that,
These are vortices.
yes, these are vortices and anti-vortices. Yes, if you're interested, the papers on archive, if you're the referee, please do that. Yes.
Why aren't they annulled? What's stabilized?
Yes, so there are 2 possibilities. There's dipolar and exchange interaction. Yeah, and depending on the type of structure, one or the other makes a stabilization. Now, what is interesting is these are already intrinsically 3D because you have 2 layers, but the 2 layers are simply anti-parallel coupled. In addition to anti-parallel coupling between 2 layers, you can also get a chiral coupling. So we know DMI coupling within the plane, the layers in a chiral fashion. You see this clockwise rotation. But also here, if we have 2 layers in an RKKY coupled fashion, coupled with RKKY coupling, we can also get the analogon of DMI in the vertical direction. So not just chiral rotation in the plane, but chiral rotation out of the plane. And that's something that was observed a couple of years ago in this paper here, as well as with Russell Calburn. And then recently we wanted to see if we can tune the strength of this chiral coupling. And it turns out we can actually, by current injection, change not just the strength, but even the sign of this RKKY DMI. So the paper is coming out in other letters later this year. And that's nice because it allows you to actually, on the fly, tune the chiral RKKY interaction. And the idea is then to actually stabilize these 3D spin structures where you have a chiral interaction in the plane and also out of the plane. And why do we do this? Well, we do this because fundamentally we are interested in 3D spin structures. So there has been some interesting work early on, some suggestions here by Russell Calburn, how to use this for memory. I'm interested in that because in our brain, every neuron is connected to 10,000 other neurons by synapses. In 2D, you cannot connect without crossing to so many neighbors. You can only on average connect to 4 neighbors this graph. But in your brain, in order to get into connectivity, the brain has gone to 3D. So fundamentally, this allows the same interconnectivity that we have in our brain also for magnetic structure. So that's what motivates this work, and we're working heavily. Okay, now, yes?
What's the mechanism behind the current change of the interlayer?
So that's a very good question. Actually, we observed this both for in-plane and out-of-plane DMI. So they're different. At the moment, we don't have a clear answer. So we speculate that it can have to do with the spin Hall effect that can act differently. But it's actually an open question. I mean, it was also found by Masamitsu Hayashi, by his group as well. So the experimental observation is robust, but we don't have a good theory yet. Okay, so second topic, how to manipulate these beasts. Now we have them in 2D and 3D. How can we efficiently manipulate? Well, and for that we can use spin and orbital torques. Well, I guess all of us know the spin-Hall effect and the inverse spin galvanic Balazs by Edelstein effect, where a longitudinal charge current generates a vertical spin current. Now, the same can also be done using orbital angular momentum. So this was predicted already some time ago, that a longitudinal charge current can generate a vertical spin current. And now what I find very exciting about these orbital currents is that in contrast to a spin current, where there is no direct coupling between the spin and the crystal momentum K, for orbital currents, you can have that. In spin currents, you need spin orbit current. It's a small effect. So in orbital currents, there's direct coupling between the crystal momentum K and the orbital angular momentum L, and that can generate an orders of magnitude larger orbital current than spin current. I'm not going to go into the details because I don't have enough time, but there are two papers here and here where I actually showed a 16 times larger torque by using orbital currents compared to spin currents. So now let's see if we can manipulate skyrmions. So here's some earlier work that we did with Jeff Eade and Peter Fischer by Xiong Wu, who drew this picture of 4 skyrmions on a racetrack, which is what we wanted to see. He took a picture, and then indeed we saw 4 skyrmions on the racetrack, and we injected currents, and everything should work. And actually, the skyrmions kind of move. But if you look closely, we actually start with 5 skyrmions, and after a few current injections, we end up with 3. So we just lost half the data. So where's all our topological stabilization? So let's do theory. In theory, everything is perfect. We have 3 skyrmions moving to the right, moving to the left. You have the skyrmion Hall angle, but they do exactly the same thing. In experiment, we have the hero skyrmion, which does what we want, moves to the right, moves to the left. We have one skyrmion that's not moving at all, and one skyrmion that's eating the other skyrmion. So here's 2 skyrmions that actually are chasing each other, and we find that these 2 skyrmions actually can annihilate if one of them is pinned. So if there's one skyrmion, it can eat the other one if it's pinned, because if you have a pinning side, you have a reduction of the DMI, which reduces this topological stabilization. So why, and now we come to the questions about the pinning. Where is all this pinning coming from? So we recently published this paper where we looked at the pinning landscape of a sample. So this is actually now over a long time, we have looked at skyrmions in the sample, and we've seen that at certain positions, the skyrmion likes to sit, and at other positions, it never arrives. So this is now a 2D structure of the landscape of our sample. And now it's a question, where do these pinning sites come from? What is the origin of this thing? And so to do that, we look at thermally activated skyrmion motion in the disk. And you see that the skyrmion is not randomly moving everywhere, but it seems to hop between different fixed positions. And we analyzed this in a lot of detail, so all the credit to Raphael Gruber, a great student who's doing that. And what he found by meticulous analysis is the following. We look at these 4 different pinning sites. We actually see that these pinning sites share a lot the position of the domain wall. So this means that the skyrmion hops, and it hops between different positions where the domain wall is pinned at certain positions. And that's also something you can expect, because the highest energy is not in the core of the skyrmion, it's in the domain wall where the exchange is high. So small changes to the material's properties will affect the domain wall much more than the actual core of the skyrmion. So here we find that the skyrmions are in characteristic configurations of the domain wall. And even for striped domains, we actually see that the striped domain with its domain wall is pinned at a particular location, which also pins the domain wall of the skyrmion. So really the pinning is at the domain wall where the energy is highest, and so the energy differences are highest. So that's really nice. And now you also understand that the skyrmions, when they hop, They hop from one position of the domain ball to the next. And in our time resolution, it looks like they are just moving from one to the other. But of course, if you look time resolved, what will happen is that one domain ball extends to a new position, and then the rest of the skyrmion will follow. Okay, so that's the reason for the skyrmion pin.
Excuse me.
Yes?
What the different color stands for here?
Yes, so these are 4 different pinning sites. So 4 different positions of the skyrmion.
How can you define the pinning side? How can you draw this circle?
Well, we just look. We look at the corner of the edge of the contrast of the skyrmion.
I did just draw the
Yes. So this is just the edge of the skyrmion. So the domain ball of the skyrmion. Yeah. And you see that the pinning side, if you draw it, actually there's a large overlap. It's not like there's one pinning side here and one pinning side here, but actually there are pinning sides so close to each other that only part of the skyrmion has changed its position. And that allows you to identify it's not the center of the skyrmion, it's actually the domain wall of the skyrmion that defines the pins.
Can you really pinpoint the position of the pinning sites?
Well, no, that's exactly the question is now here. We have this area where you overlap. Where is the pinning site here? This is something we don't know because it could be anywhere here. Yeah. Because there are 2 forces. There is the local pinning site of the domain ball, and then you have the force that wants to make the skyrmion round to reduce the length of the domain ball. So these together will actually lead to the actual shape. So it's correct. We don't know if it's here or here or here, but somewhere in this area, because that's where you have the overlap. But it still allows you to identify that there are some areas, for instance, here, it must be somewhere here where there's overlap, or here must be somewhere here. So you can see roughly where the pinning site is. Of course, the next step is, and if you have any students here who are hardworking, find out what is the real pinning site. Combine this with structural imaging. We're trying that, but it's very challenging. Okay, now we come, unfortunately, this movie is not running because it's not on my computer, but what you would see here is now, if we reduce the pinning, we can have viscous motion of the skyrmions rather rapidly. And what is very important is that we actually see a motion that is 10 billion times reproducible. So here we have moved the skyrmion 10 billion times completely reproducibly back and forth by reducing the pinning. And we also find the skyrmion Hall angle, already introduced previously. Currently, skyrmions don't move along the current direction, but under some angle. And the skyrmion Hall angle changes with velocity, which was not predicted by theory. Theoreticians said it should just depend on the size. But actually, the group of Buxton Hoffman last week found this independently and published it back to back. And the question was, what is the theoretical explanation? They had a theory explanation based on creep. And this is actually valid in the creep regime. And we had a based on pinning, valid in the creep regime, and we had a theory based on skyrmion deformation, which is valid in the viscous regime. Meanwhile, there's a lot of nice work on that by Charles Reichert and family, as well as other groups. Okay, so skyrmion motion 10 to the 10 times rapidly is possible, but we cannot make a racetrack that is actually programmed. So actually, I gave up on memory because there's too many incumbent memory devices already existing. So I went to non-conventional computing because there's no competition already in the market. So, but it's also very interesting. So instead of doing rapid and reproducible dynamics, we actually want to go to very high efficiency. And so how can we go to high efficiency? Well, you can go to high efficiency if you don't use currents to move things, but in your brain, we also exploit thermal excitation. So here's actually a movie, which unfortunately is not running, where we inject current pulses and we move the skyrmions from right to left. And when we do this, we actually observe that not only with the current we can move them, but we also see a wiggling around. And this was done in a stack, which was developed based on this nice paper here, where we have ultra low, oh no, you see it. We have ultra low pinning, and we see that skyrmions wiggle up and down. And initially, I thought that cannot be. So because there was a theoretical prediction that diffusion should be actually suppressed, and I always believed theoretician, but the students did the experiment anyway, and they saw that they're moving around, and I said, oh, that must be wrong, then maybe you're doing something wrong with the current injection. So I told them, just switch off the current, switch off the field, and observe. And this is what skyrmions do if you don't look at them. I actually do look at them. They just move around. And I should point out that we initially also started to track these skyrmions by hand, just using pinpointing. Then we used also image J, like Jin is doing. And now we're actually using just very nice machine learning. So there's very good machine learning. So we use UNet, which is a recurrent neural network, convolutional neural network, which is amazing at detecting it. And also it works weekends. And it's much better than a bachelor student. An experienced postdoc is still better at tracking than the UNet. The paper is on archive. I didn't put it here, but I can only recommend you to use this. Actually, it was developed. The network was developed for detecting red blood cells. And apparently, Skyrmions are very close to red blood cells in the contrast. So it's amazing how well it works. And as I said, you can track billions of Skyrmion trajectories for free, overnight. Anyway, so when we looked at this, we wanted to check if it's really Brownian motion, and we looked at the mean square displacement, which is completely linear in time. And this is published here and also reproduced in this nice work here by the Strengths group. Yeah.
So other Skyrmions are moving, but what I wonder why far left.
That's sitting in a pinning site. So where you have to wait longer. So it's thermally activated processes, so it's exponentially dependent on the height of the energy barrier. So you have to wait for longer. Eventually it'll also move, just a question of when. Also, this was nicely produced by Uli Novak using atomistic spin dynamics simulations. And then I got excited by these papers here where Daniele Pinner, Karin Eberscher-Sitte said that you could use this for unconventional computing. 5 years ago, I had no clue about unconventional computing. But I got excited. And then they said, well, what you have to do is you have to do fast dynamics. And well, this is real time, so this is pretty slow. How can we get it faster? Well, actually, what we can do is we can do some AC excitation, which then changes the diameter of the Skyrmion and then depins it. And then you get like a 300 times higher Skyrmion thermodynamics, which is published in Advanced Materials in this paper here. And this allows you to tune the velocity or the speed of the thermal excitation. And also it allows you to always depin the Skyrmion. So we get into the regime of free Skyrmion diffusion. No more pinning. We have a flat energy landscape, effectively flat energy landscape due to this excitation. So if you're interested, have a look here. And then finally, to increase the thermal excitation dynamics even further, we went to synthetic antiferromagnets because theory predicted there should be a factor 10 to the 5 faster thermal Skyrmion diffusion in synthetic antiferromagnets. And we then at least found a factor 10, 10 to 5. Okay. Well, experiment as usual is not as nice as theory. But if you're interested, here's the paper by Takashi Doi, who's an excellent postdoc now, assistant professor in Japan. And if you're the referee, it's be nice. Okay. Now, finally, unconventional logic. So I told you that we are interested in using these Skyrmions. And I should say that I'm going to show you 3 examples of unconventional logic. And the concepts, none of this is ours, we just did the implementation. And the first one is stochastic computing. So who is a specialist for non-conventional computing in the room? No one, that's good, because neither am I. I'm always afraid if there's like a computer scientist sitting here that will ask me about algorithmic questions. Okay, so stochastic computing is a non-arithmetic way of calculation using random bit streams. It is approximative with progressive precision. And it's a simple way of multiplying numbers using just AND gates. And you can do a few other functions such as scale division. And it has a problem in that we need unbiased, uncorrelated bit streams. Now, this sounds very fancy and typically no one understands. So let me walk you through this slowly. Okay, what do I mean by bit streams? So if you have a 501 coin, or this time it's euro coin, you have heads and tails. Chances of heads is 50%, chances of tails is 50%. So if you do this, flipping the coin many times, you get a bit stream where you have heads and tails, 0, 1, 0, 0, 1, 1, 1, 1, 1, and so on. And you have 50% are zeros and 50% are ones, okay? So this bit stream here actually represents 50% or 0.5. Now, if you have 4 cards and the chance of drawing an ace is 25%, Then the bit stream is it's non-ace, 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 ace, non-ace, ace, ace, and so on. So this bit stream here, which has 25% ones and 75% zeros, corresponds to 0.25. So with this, we can actually represent any number between 0 and 1. Okay, so this is a bit stream. Now we can use our two bit streams, and we can feed it into an AND gate. And then I get 0 and 0 is 0, 1 and 0 is 0, 0 and 0 is 0, 0 and 0 is 0, 1 and 1 is 1, and so on. And it turns out that the result of the AND gate is the multiplication of our numbers. So 0.5 times 0.25 is 0.1. So this is now an easy way to multiply numbers. But there's a problem. And the problem is that this is only correct if the bit streams X and Y are uncorrelated. So what does that mean? So suppose we have two bit streams, one corresponding to 0.75, one corresponding to 0.2, 0.5, and then we feed them into the AND gate. 1 and 1 is 1, 1 and 1 is 1, 0 and 0 is 0, and so on. It turns out that the result is 3 over 8 is correct. 6 over 8 times 1/2 is 3 over 8. Great. But if we now put in two identical bit streams, 6 over 8 and 6 over 8, then the AND gate also gives 6 over 8, and that's obviously wrong. 0.75 times 0.75 is not 0.75. So if they're completely correlated, it's wrong. So what we need to do is, we need to flip the positions of the ones and the zeros while keeping the total number of ones and zeros constant. And then this allows us to decorrelate the two input streams. And there's no good CMOS device we are aware of that is low power and allows you to decorrelate bit streams. So this is what we did based on this suggestion of the little pinner. So here we have our reshuffler decorrelator. So we have two reshuffler chambers. And what we do is we nucleate Skyrmions here and here. And if you nucleate one here for 1, you nucleate one here for 0. Here we do readout by imaging, but eventually you do it electrically. When the Skyrmions enter the chamber across the blue line, then it's an input stream 1 and input stream 0. And when they exit the chamber here, it's an output stream 1 and an output stream 0. And now you can see here, Skyrmion enters, so it's a logic 0. Skyrmion enters here, it's a logic 1. Now the first Skyrmion will exit here, it's a logic 0. Now another Skyrmion will exit here, it's another logic 0. Now a Skyrmion will exit here, it's a logic 1. And then we have this input stream and the output stream. And now the important property of our reshuffler chamber is that they thermally activate the Skyrmions to diffuse around this chamber. So the time it takes from here to here is not constant. Sometimes it's faster for a Skyrmion here, sometimes it's faster for a Skyrmion here, and so the order of the ones and zeros shuffled around. But since all the Skyrmions entering here eventually exit here, and all the Skyrmions entering here will eventually exit here, this means the total number of ones and zeros is conserved. And we can actually analyze this and we find the p-value is completely conserved, meaning no Skyrmion got lost, but the correlation is down to 11%. So we have perfect p-value retention and good correlation. And then we published this in Nature Nanotechnology, wanted to make the cover page. We failed, but Andreas Donges made a really nice picture, so this is our shuffler which you get to see. And now what we can do is we can feed this into an AND gate, and then we can multiply using probabilistic computing. Now this is working, it's good, but the question is who needs multiplication? So it cannot do much else. It can do multiply and scaled addition. So the question is, it's not universal. Can we make a universal computer? Turns out we can using token-based Brownian computing. That's an approach which has been pioneered already many years ago, which is based on tokens, which are discrete signal carriers that make random walk, make a random diffusion. You can use Skyrmions, you can also use mice. Mice are more expensive and need to be fed, so we use Skyrmions. And then you feed them into a circuit with certain transition rules. And then in this circuit, they do the calculation, and then you get some output, and this is what you then get the result. So the actual circuit comprises 3 different three different components. The hub, where the skyrmion can thermally activated go in and go out in any direction. The ratchet, where the skyrmion can go only one way and not back. Actually, it's not needed, but it speeds up the calculation. And the C-join. The C-join is where the calculation happens. C-join is a component where if one skyrmion enters, it exits back to where it came from. And if two skyrmions enter at the same time, they exit through different exits. And so if you do this, you can, for instance, make a half adder that was shown here. We made one crossing free, and then we can calculate how long it takes. And by typical thermal activation, our skyrmions, it takes like a minute or so for the half adder to be performed. But if you do like induced dynamics or even synthetic antiferromagnetic dynamics, you can get actually sub-microsecond operation. Now, the advantage is it's very low power because all the motion is random, just thermally activated, no need to inject any currents or anything. The disadvantage is that it is thermally activated, meaning that if you're unlucky, the skyrmion will for a very long time just randomly go back and forth and not do the calculation. So while the average time to get the calculation is okay, it could be sometimes you wait for ages. So this is only good for an application where you don't care when you get the results. So I'm not so sure how many of those are around. So the third part I want to show you is maybe the most useful one. It's called reservoir computing. Now, reservoir computing is an approach which is used to map a complex problem into a linearly solvable. It's used very widely for pattern recognition. And it actually contains some input. It contains a recursive or recurrent neural network and some output. Now, the advantage of the reservoir computing is that in contrast to a typical recurrent network where we train the weights in every connection, here we only train the output weights. Whereas this one here is a physical implementation with fixed weights that we don't train. And this overcomes the training constraints, so it's much easier to just train a few output weights instead of the whole reservoir. So what it does is it projects different events into a higher dimensional space. So let me show you an example. Here I would like to classify the different colors, green, red, and blue. Now, please give me a linear line that makes all the blue points on one line and all the red on the other. There's no way you can do that. But if we now project this into a high dimensional space, we can use some hyperplanes which delineate the blue dots all here, the green dots all here, the red dots all here, so they can be easily classified. So that's what the reservoir does. And so we use Skyrmions, so all the credit to George Marianoff and Karin Evershed-Witte for coming up with the idea of using Skyrmion fabrics as a reservoir. You have some inputs, for instance, can be current. You have some outputs, which can be magnitude resistance sensors. And then you can determine the change of the reservoir to the input, and then use that to detect certain input. And we thought this was too complex, so we just went for a very simple triangular structure with a single skyrmion inside. And what we detect is a voltage which we apply on these three inputs, which can be plus, minus, or zero. Plus, minus, or zero, plus, minus, or zero. And so now what we do is we inject a current. So without any current, if they're all at zero or all at plus or minus, the skyrmion is in the center because it's repelled from the edges. If we inject current like this, then we get the skyrmion pushed towards this edge, current like this, skyrmion pushed to this edge, current like this, skyrmion pushed to this edge. And we can use, we mimic 4 TMR readouts. And from this, we can now detect the different inputs. And so as the first try, just so as a proof of concept, we actually implement Boolean logic. So just the inputs A and B, we do an AND gate, or NAND NOR. And what is important is that here we actually have a non-linearly separable function. So XNOR cannot be implemented by a simple feed-forward perceptron. But you see it works. We see here 0 XNOR 0 is 1. 0 XNOR 1 is 0, 1 XNOR 0 is 0, and 1 XNOR 1 is 1. So this works, and it allows you to actually make an operation that goes beyond the power of a simple perceptron. you're interested, here's the paper. Now we're doing many more things for time multiplexing, not just spatial multiplexing, but my time is running out. So let me give you the most important slide. This is the people that did all the work. I didn't do any of this. This is what we looked like before Corona. This is what we looked like during Corona. At the end of Corona, no more Corona. And I should in particular point out the permanent staff scientists, Gerd Jakob, Martin Jordan, and Lars Fönter, as well as our theory colleague Peter Werner, a lot of excellent students and postdocs, which were all in the pictures. Also, science would not work so fast without collaboration. So initially, a lot of the work was started by Simon Wu and Jeff Beach's group. Here you work with Peter in Konstanz, also in the earlier work with Peter Fischer, and then we worked with Jonathan Lilliard and Bastian Weinberger. A lot of the work was done at synchrotrons with Simon Wilson, my former student, and Jan Rabe, and also for collaboration with Hermann Stoll, Jaroslav Zweigert, and the group of Gisela Schütz, and Stuttgart and Bessie. Here is the part from Herrn Gonai, Peter Werner, Daniela Pinner, Kaina Vashiseta, was Nobel University in Mainz, and also nice collaboration with colleagues in Jerusalem and the ERC Synergy Grant 3D Magic, as well as my second affiliation with NTU in Norway with Arne Pratas and Alives. Of course, nothing would work without the funding, so I acknowledge the German Research Foundation, the ERC, QSpin, Material Science and Minds, you and companies. And with that, I summarize. I've shown you that DMI stabilizes chiral spin structures with a defined topology, and we find that Skyrmions are pinned at domain walls. Here are the relevant papers. I've shown you that Skyrmions can move very rapidly, but also completely reproducibly, what is needed for a Skyrmion racetrack, and we identified the origin of the Skyrmion Hall angle. Here are the relevant papers. And I've shown you that we can use thermally induced diffusion in synthetic antiferromagnetism in particular. They can be used for probabilistic logic, and we can generate low-power token-based Brownian computing devices and reservoir computing that can at least do some Boolean logic. Again, here on the papers. If you're new to Skyrmions, there are some interesting reviews. This one and this one and this one. Also, if you're interested about ultra-efficient manipulation using orbital ports, there's a review from Dr. Folger himself. And with that, I just want to point out that if you're interested in topological solitons, we actually have a research center on dynamics and topology. Have a look at the website. If you want to come and visit us, we also have some money to invite you. So let me know. And if you're interested in the slides, I'm also happy to share them. And with that, I thank you for your attention. And that was the research.
Maybe just two questions. In Skyrmion moving and then excitation. So, what is the chance that it will be destroyed at the boundary because you inject the Skyrmion and then there is a region where the thermally excited Skyrmions are there. At this boundary.
If it's annihilated here, we lose data. Yes. So indeed, so what we found is experimentally that within the time frame that we analyzed, we didn't lose a single Skyrmion. And in general, we find that when you have Skyrmions which are very low, have very low pinning, they actually never annihilate. So they play billiards. They bounce off the edge, they bounce off each other. So in this case, we don't see any Skyrmions which are annihilated. Now we're still injecting a current to move them across here. And if we drive the current very hard, then it can happen that we can annihilate the Skyrmions. But then there's two things which are good and bad. The bad thing is, yes, you'll lose data. The good thing is that since you have a long bit stream, in the infinite time limit, 1 bit lost doesn't matter. The value that you encode, let's say 0.5 or 0.25, only change a minute bit, or a minute small amount if you lose 1, 0, or 1, 1.
And second question is can it be also applicable this concept for other exciting sums, topological what is this?
Oh, absolutely. There's nothing particular about the Skyrmions. I mean, anything that you can put in here, you can get out. So vortices are not so ideal because vortices, you cannot combine vortices without anti-vortices because you have around at the edge, you need some pick. But Merons, anti-Meron, higher order Skyrmions. So everything that is a token, is a point-like particle, can be used. But vortices won't work so easily because vortices are not confined. But other topological spin structures.
I have one technical question and one general question. The technical question is that in a pinnings, hopping from the pinnings, have you measured the topology by using the AFM or
Topography.
topography?
Yes.
Topography of
Yes.
the temp?
Yeah. So So that is an extremely important point. And it relates to where does the pinning come from? Yeah. So typically we don't see in AFM defects. So we think since the stack here contains polycrystalline heavy metal, that it's grain boundaries, which are very difficult to detect. So now what we want to do is we want to combine high resolution TM imaging. But as you know, this is also difficult. So, I mean, yes, for all the students out there in the world, if you want to make a big impact in magnetism, find out where the pinning comes from and fix it. It's an extremely important problem. It's also a challenging one, but correlating magnetic changes and structural changes, I think is super important. I guess you agree.
Another question is you showed the many unconventional computing architectures. So, could you comment on what is the challenges that we should overcome to realize, to make the real device by using this concept?
Okay, I think there are two challenges. I mean, for me, at first, this is just exciting science. You need to find a problem that can be efficiently solved by a particular approach. So we have now actually collaborate with a company that have a problem for us, and we think that maybe we have a good solution for it. But I think very often in science, we do solutions in search of a problem. So we need to have a real-world problem that is most efficiently solved by this. And I think if I look at this, okay, the stochastic computing, multiplication, scaled addition, maybe there are certain, regions where you need this, but it's not universal. For the token-based computing, well, you need something where you don't care when you get the solution, not clear if that really is very broadly applicable. But I think for the reservoir computing, there's a lot of interest because it is very universally applicable to pattern recognition. And typically, standard CMOS implementations for pattern recognition are not very efficient. So if you have some problems that can be mapped into this input-output, then I think there is, like for optical pattern recognition, like these type of networks are used. Reservoir computing is now widely developed, not just with magnetics. One should also point out the disadvantage of all these non-conventional computing for us is that there's a lot of competition out there from resistive switching people, from photonics and reservoir computing. A lot of optical stuff is being done. So it's absolutely not clear that magnetism is the best hardware solution for this, but just the one that I'm good at, or relatively good at. So I'm just trying to explore, is there like an implementation where magnetism is a natural solution? And maybe there is, maybe we'll be beaten by some other hardware, and that's okay. The better solutions are the enemy of the good solutions. So yeah, so that's my answer.
Thank you.
Yeah, so considering the Skyrmion motion, you mentioned this creep regime for the small driving current and the viscous motion for the high driving current.
Yeah.
So could you go over again, like what's the different mechanism for these two different regions?
Yeah, so fundamentally, creep is defined by waiting time. So creep means you are in a pinning site, you wait for a long time, and then you rapidly hop to the next pinning site, you wait, and you hop again. So the speed going from one pinning site to the other is negligible. The time of that is negligible compared to the waiting time in the pinning site. So that's why it's governed by this exponential dependence, because you have an exponential dependence on the energy barrier height. And so it's the waiting time that governs everything. The viscous flow regime means that you have so high drive that you overcome all the pinning sides, and the average speed is governed by the driving force, not the pinning sides. So that's the two different regimes. Where the transition is depends very strongly on the strength of the pinning, and of course the drive as well. But it's very interesting because then you have different scaling laws and so on. So it has been studied actually for domain laws. There's a lot of literature out there from people in Paris, for instance, where they studied, Peter Mathias did a lot of nice work, where people studied this transition from creep to the depinning regime to the viscous flow regime. It's also interesting from a statistical mechanics point of view. So if you send me an email, I can send you a lot of literature. So we're absolutely not the first to do this. So like, you know, Capgen already did like 10 years ago, and all of them that work on it. And even before domain walls, there's a lot of literature on them. So.
I'm a researcher from the field of supergrid. The pinning can be important for
Vortices.
for text. Skyrmion can be chiral domain or something. And I wonder what is the property of pinning of your system? For example, pinning can magnetization locally or something. What is the property?
So since we know that the pinning side pins the domain wall, then likely what is a very efficient way to pin a domain wall is a local change of the exchange interaction or the DMI. Possibly also anisotropy, but small changes in DMI or exchange act as very efficient pinning sites because the exchange energy is highest at the domain wall, because that's where you have a change in the orientation of the spins. And therefore, a small reduction in the exchange energy would make a very efficient pinning site for a domain wall. So
I don't know what mean exchange or
well, I mean, okay, exchange is like the alignment of the force that the interaction that makes two spins go parallel. And if you're at the domain wall, the spins tilt. Yeah. So if you have a reduction in the exchange energy, the exchange integral, then it's cheaper, energetically cheaper to tilt the magnetization. And therefore, the domain wall where you have a tilt in the magnetization will be located at a position where it's energetically favorable, and that's where the exchange flow.
So you mean property of pinning can be understood as some sort of magnetic
Property,
right?
yes.
Effectively.
Yes, so change in local magnetic property can make pinning. That's our interpretation.
Yeah, okay, let's think of the speaker again.